Hello, I'm Jinsong Park. I'm honored to give a presentation about our paper, Rethinking Data Augmentation for Robust LiDAR Semantic Segmentation in Adverse Weather. I'll start with a summary of our contribution. First, in our work, we identified the main factors causing performance degradation in adverse weather. And second, we integrated the types and severity of adverse weather in data-centric manner. And as a result, we address the challenges of synthesizing specific weather types and severities, and set a new state-of-the-art on semantic SDF. In this presentation, I'll talk about how we set our problem statement and found out main factors of adverse weather in toy experiments, and then talk about how we resolve the issues in methods and experiments. Let's talk about problem statement first. Most datasets for driving scenes with LiDAR, such as Kitty or NU scenes, are collected in clean weather. The data acquired in clean weather tends to have low noise and well-aligned points. However, LiDAR data collected in adverse weather conditions, such as rain, snow, or fog, often seems noisy and poorly aligned points. Like shown in this figure, for example, rain, snow, and fog data. This discrepancy between clean and weather condition data leads to performance drop of LiDAR perception, such as LiDAR semantic segmentation. Someone might consider simply achieving more data under this weather condition can solve this issue, but this problem is not feasible. This approach is not feasible because there are many types and severity in adverse weathers. This is why previous research focused on simulation or domain generalization methods. However, weather simulations require substantial computational resource and must be done before training. Also, task-agnostic domain generalization methods do not fully address the specific data distortions of adverse weathers. Therefore, we aim to identify the main factors contributing to a performance drop of LiDAR segmentation in a data-centric manner, and we try to utilize these main factors to generate weather condition data without the need for precise weather simulation. Let me talk about how we found the main factors of degradation. In previous research on weather simulation for LiDAR data, for key physical phenomena were identified: point drop, occlusion, and geometric perturbation, and intensity distortions. Our goal was to identify what is the main factor of performance drop within them. To do this, we did toy experiments with pre-trained MenQ-Net. The results revealed that point drop, occlusion, and geometric perturbation led to most significant performance degradation. We also found similar results on qualitative results. In our analysis, we interpreted occlusions is same as point drop because points disappears in localized regions where convolutional operations applied. And so we identified main factors of weather conditions as geometric perturbation and point drop. Next, in our methods, we have identified the two key factors, geometric perturbation and point drop. We can interpret these operations as transformation of clean LiDAR data into weather condition data. And if these operations work adverse to LiDAR segmentation model, we can effectively copy the effects of real weather conditions. To do this, first we implemented selective jittering to describe geometric perturbation. This technique perturbs point coordinates within random regions while maintaining consistency in depth and azimuth angles to preserve model's performance in clean weather conditions. And our second proposed method is learnable point drop. We use DQN to find adversarial point drop which hinder LiDAR segmentation. The state is set by the loss and entropy of LiDAR segmentation model, and DQN is rewarded based on the increase of them. The overall process is as below. we first apply our selective jittering to the input points and obtain loss and entropy. And learnable point drop model drops points that are likely to hinder LiDAR segmentation model. The LiDAR segmentation model then trains to become more robust against these drop points. And finally, the learnable point drop model is rewarded based on their increment of loss and entropy. Our method achieved state-of-the-art performance on the semantic STF at the time of the submission. Thank you for your listening. See you at poster 149.